Okay, thanks, Shanka. I'm Wenda. I'm Wenda Li. I'm a final year PhD from Cambridge, supervised by Professor Larry Paulson. And the topic today is about evaluating violin numbers through Cauchy indices in Isabelle. More specifically, what I will cover today is a novel tactic for violin numbers, which I believe will greatly facilitate reasoning them formally in Isabelle, and also a novel verified procedure to count the number of roots in Isabelle. And the paper for this development is still in preparation. The source code should appear in the archive of formal proofs very shortly. So first, what is a violin number? A violin number is is the number of times that a path travels counterclockwise about a point. So in this case, we have a path gamma, which is essentially a continuous function from real to complex. And that's point A. And we can see that gamma actually travels clockwise about A for exactly one round. So here, the violin number of gamma A is -1. And for point B, gamma travels counterclockwise about B for exactly one round. So here, the violin number of gamma about B is 1. And C is actually outside gamma. So here, the violin number of gamma C is 0. Formally, we can define the violin number using some contour integral. Actually, this is the definition we use in Isabelle. And now you may ask, why do we care about violin number and its evaluation? This is because violin number is an important object in complex analysis, and it is ubiquitous. It will be hard for us to avoid reasoning with violin number if we want to do formal reasoning in complex analysis. Here is a motivation example. In a previous formalization of mine, I want to formally to evaluate this improper integral. And the approach I was using is to embed this problem into complex plane. So, and by defining two paths, one is a linear path, LR, one is a semi-circular path, CR, and here gamma is LR concatenated by CR. So here the plus here is path concatenation. Then we can convert this improper integral into some sort of contour integral. And by the Cauchy's residue theorem, which is already in Isabelle, we can then evaluate this contour integral using residues and violin numbers and solve this problem. In this case, these two residues are relatively easy to evaluate, but actually these two violin numbers cost me quite some trouble. Here is what I did. For the first violin number, I defined the auxiliary semi-circular path, CR prime, such that CR plus CR prime forms a full circular path, and the violin number of CR plus CR prime about I is 1. This is because this point I is inside this circle, and there's a lemma in Isabelle which can show this very easily. And then I show that the path CR plus CR prime and LR plus CR prime, I mean these two paths, they are actually homotopic on the plane of complex numbers minus the point I. Hence, in this case, there's a lemma in Isabelle which says that these two varying numbers should be equal, and hence we can conclude the proof. This is for the first varying number. For the second varying number, I defined another auxiliary class, which is the ray, starting from minus imaginary, which from this minus I to negative infinity. And then I show that this ray does not intersect with this LR plus CR. And by a lemma in Isabelle, we can have that the real part of this varying number is less than 1. And because this LR plus CR is a loop, in this case, this varying number is an integer. So we can then conclude that this varying number is 0 as we planned. As you can see, despite the fact that these two varying numbers are very easy for humans to evaluate, we can clearly see that by definition, this should be 0, very straightforward. In textbooks, these kind of proofs are strictly omitted. But in Isabelle, actually, to show this formally, it is not very easy. And my previous proofs are ad hoc and non-systematic. Most importantly, these proofs, they don't generalize. So I began to wonder if there is a better, systematic, uniform way to do this kind of unification, to do this kind of evaluations. The answer is yes, and through approximation. In a very simple case, suppose we have a path gamma, and we know that gamma crosses the imaginary axis exactly once, and the intersection point, gamma t0, the real part of it, it is greater than 0. In this case, by our intuition, we know that the argument change of a point traveling through this gamma should be between 0 and 2 pi. And in this case, and hence, the real part of this varying number is between 0 and 1. That is, we can approximate the real part of a varying number by the way it crosses the imaginary axis. To make it more precise, we can define a function f as the imaginary part of gamma divided by the real part. And the image of f as a point traveling through gamma should look something like this, where f jump from positive infinity to negative infinity near this point t0. This is because we know that the real part of gamma t0 is 0, and f is positive before t0 and negative after t0. So more formally, we can define the function jump. So jump is if f jump from positive infinity to negative infinity, then it is -1. Then in other case, if it is from negative infinity to positive infinity, it will be 1, otherwise it will be 0. In this case, we can have that the jump of f at t0 is -1. By summing up those jumps, we can define the Cauchy index. And we can formulate our previous intuition into an inequality. where we can approximate the real part of a Wenda number using Cauchy, using some Cauchy index, like this. Furthermore, if we also know that the path is a loop, and we can even evaluate this Wenda number, evaluate this Wenda number of t, of the Wenda number of gamma about z0 is actually, we can evaluate it using the Cauchy index of gamma about z0. And this is because gamma is a loop, and we know that this Wenda number is an integer, and by definition, this Cauchy index is an integer as well, and combined with this inequality, we can then evaluate, we can do this evaluation. And now, with this new strategy, we can have an alternative proof for the Wenda number. That is, we can reduce the evaluation of a Wenda number into evaluation of Cauchy indices, like this. And especially in this case, because the structure of LR and CR is very simple, and evaluating the Cauchy index of LR and CR is very straightforward in this case. And more importantly, this kind of proof is more uniform. It is systematic and it can generalize. So for general cases, I have built a tactic which reduce evaluation of Wenda number into evaluation of a bunch of Cauchy indices. When each of these subpaths is either a linear path or part of a circular path, evaluating the Cauchy index, evaluating its Cauchy index is really straightforward. Okay, that is my first part, which is about the tactic to facilitate reasoning of Cauchy, of Wenda numbers. Now, let us come to the second part of my talk, which is about the number of roots. I guess you may have a question that what Wenda numbers has anything to do with the number of roots? The answer is, thanks to the argument principle, we can decide the number of roots within some domain using some kind of contour integral. And here this p prime is the first derivative of the polynomial p. And more beautifully, by the definition of Wenda number, we can have that the Wenda number of p composed with gamma about 0 is actually equal to this contour integral, and hence again we have Wenda numbers.
These numbers without multiplicities, or
yeah. So this is number of roots counted with.
Otherwise, number of roots is a degree of the polynomial.
Sorry.
Is it counted with multiplicities?
Yeah.
Or without multiplicities?
With multiplicity.
But the p prime of the p has only simple roots.
The simple powers.
You just cancelled all the multiplicities by having p prime over p. No?
Not really. I have formalized this argumental principle in Isabelle.
Oh, sure.
So actually so in this case, n should be the one counted with multiplicity.
The simple powers and the residue is the multiplicity, so there's also up to n.
There's a
But
formal proof.
the roots, the poles are all simple, right? For p
The
prime.
powers are simple, and the residue is the multiplicity, and the multiplicities add up to n.
Okay.
So to count the number of roots in a rectangle, we can define 4 ordinary paths, linear paths along the edge of this rectangle, L1, L2, L3, L4. And then, once again, this number of roots, we can evaluate, we can decide the number of roots through Cauchy indices. But here we may have a problem that with this, with the path of P of L, recall that previously I said if a path is either a linear path or part of a circular path, its Cauchy index will be very easy to decide. But in this case, this P of L is neither, and can we still evaluate this Cauchy index? The answer is yes. And thanks to the Sturm task set, we can actually reduce this evaluation into some remainder sequences. Here, Q1 and Q2 are the real and the imaginary part of the polynomial P of L. So you see the left-hand side of this equation is actually we can execute it. Based on this idea, I have built a verified procedure to count the number of roots within a rectangle. Here, for example, to count the number of roots of this polynomial, within this rectangle, and we can type this following command, which will return 2, as this polynomial has exactly 2 roots within this rectangle, and the roots are the I with multiplicity 2. Very similarly, I have built another verified procedure to count the number of roots within a half plane. And you can see that by typing this command, we can decide that this polynomial has exactly 2 roots within the left half plane of the imaginary axis. So this kind of problem is actually related to the so-called Rawls-Hurwitz stability criterion in control theory, where we need to decide whether all roots of the characteristic polynomial of a linear system are located in the left half plane of the imaginary axis. So, and this is one of the reasons I try to count the number of roots within this domain. In the future, if necessary, we can try to count the number of roots within other domains, like circle or sector, based on this very same idea. To remark, this whole development is about 13,000 lines of code, and took me about 7 months to finish. And the thing that troubled me the most is actually the subtlety in mathematics. In fact, the Cauchy index, the definition of Cauchy index I presented in this talk is the one used in most standard textbooks, but it is not the one I used in my own formalization. Because I need to cover because I need to generalize the definition and to cover some corner cases which are not even mentioned in the standard textbooks. And I can still recall that I told my supervisor Larry at least 5 times that I'm going to finish my formalization within the next 2 weeks. But in the end, it took me far more than I expected. Okay, so to conclude, in this talk, I have covered 2 things. One is a tactic to evaluate the Wenda numbers through Cauchy indices. And the other one is to count the number of complex roots in some domain. And this development, I believe, will greatly facilitate the reasoning with Wenda numbers in complex analysis, and will also lay a foundation for future formalizations in computer algebra. Okay, thanks for your attention. Any questions?
Questions? Yeah.
What happens if one of the zeros is on or close on the...
Is on the path.
Yes,
Yeah,
or very
exactly.
close to it. Or very close to it. If
Close
it's very
or
close
very
to it,
close to
you
it.
should also have problems.
It's on the path or close to it.
Yeah, the paths have to be close.
No, near the path, near the border.
Near the border, that should be
If
fine.
the root is very close to the path.
Okay. Because the nature of my formulation is symbolic, so if the point is near the path, it will be okay. But if the point is right on the path, then I leave it to the future. So this will be a problem, especially for this rectangle case. But for the half plane case, actually I haven't done it, but it should be not very hard. We can actually try to eliminate the greatest common divisor of the real and the complex part of the polynomial. So in this case, it should be easy to handle a case where there's a point, there's a zero or root on the other.
Not so easy.
Yeah.
Any other questions?
Next
We see some
one.
code.
Huh?
We see some code.
See some code?
Yeah. Did you bring code with you? I think this is the question.
This.
I think that we should do at the mezzanine. Yeah, so
Will you be around for a demo?
Can you do a demo?
Which demo? What?
Can you do a demo in the
Oh, yeah.
main?
No,
Not
no,
now.
No. Sure. No problem. I have the
Okay.
code in my laptop.
Okay, let's thank him again.